This will be the semester test, the midterm. So the midterm will be the same as the Chapter 4 test. Now, what we're covering in Chapter 4 is polynomial functions. Now, polynomial functions, we've covered them a little bit. Quadratics, what we covered in Chapter 3, are considered a polynomial function. But when we talked about quadratics, we were really just talking about equations that the biggest variable or the biggest exponent was x squared. That was the biggest term that we had. Now, with polynomial functions, we can have variables with powers greater than 2. We will have some with a power where we do have x squared as the biggest variable, but we can have some that are bigger. All right, guys, so this here, a sub n, x to the n, plus a sub n minus 1 times x to the n minus 1, plus dot, 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 all the way to a sub 1x plus a naught, is just the general way to write any and all polynomial equations.
So you got to write that out before you can do it?
No, this is just the general form, because a sub 1, a sub n minus 1, a sub 1, and a sub 0 is just a way to signify a number. It could be the same number, it could be different numbers, but each one of those is just a number. And for like x to the n, well, that could be x to the 7th. Because n is just going to be a number, so we have x to the 7th. Well, x to the n minus 1, well, that would be 6, because 7 minus 1 would be 6, and then we would have a term times x to the 5th times x to the 4th times x to the 3rd, and then we would have x and naught. So this here is just a general way to write any and all polynomial functions. So no matter what the polynomial function is, this is the general representation of it. Now, there are 4 specific types that we'll look at here, well, 5, based off degree and type. Well, if the degree is 0, we consider it to be a constant function, because we would have x to the 0, which really tells us we don't have any variables. We just really have the equation like f of x is equal to negative 14, or equal to a number, any number, would be considered a constant function. Well, when the degree is 1, it is linear. Just the equation of a line. 5x minus 7 would be a linear equation, or any other equation of a line. Would be a degree 1. Now, degree 2 would be a quadratic, which we spent a good bit of time in Chapter 3 talking about quadratics. And they provided us with an example of a quadratic. Now, degree 3 would be a cubic function. Well, here's an example of a cubic function, and the reason we know it's a cubic is because the biggest variable is a 3. So the degree is 3, and it is a cubic function. And the last one that we have here, well, I'll just pick this color, is 4. And 4 would be a quartic, and the reason we know it's a quartic is because the biggest exponent is a 4. All right. So any questions on this here so far? So this is really talking about degree and type. Well, help. Now, standard form. When we write a polynomial in standard form, we write it in decreasing power. So the exponents are going to start with the biggest on the left and decrease going to the right by 1 or going down. And we'll have the smallest power, or the number without 1, the constant term, last. And the leading coefficient is going to be the number in front of the term with the highest power. The number in front of the variable with the biggest power will be the leading coefficient. So, now before we start looking at examples and defining degree and leading coefficient, it'd be nice to know and kind of define what a polynomial is. And really the best way to define what a polynomial is, well, defining what it is not. Because if it doesn't classify as one of these here, then it will be a polynomial. Now the first thing that we can say a polynomial is not is that it can't have negative exponents. So we can't have x to the negative 4, or a negative number. the exponents will not be negative. The exponents will not be negative. Another thing is that the exponents cannot be fractions. So we can't have x to the 2/3. Exponents are not fractions for it to be a polynomial function. The third one, variables are not inside a radical. So the square root of x. Now, if it can be reduced all the way, then we'll need to reduce it. So like the square root of x squared is just x. That would not be the case. But if we are not able to get the radical out of the x, or the variable out of the radical, then it just doesn't work. It's not considered a polynomial function. It would actually be considered a radical function. Variables are not in a radical. We have 2 left, or well, 3 left. Variables are not multiplied together. So we can't have x times y. We can't have 2 variables multiplied together. 2 different variables being multiplied together. And lastly, variables are not in the bottom of a fraction. Variables are not in the bottom of a fraction. Now there is one that we do need to add, and that's exponents are not variables. Exponents aren't variables. And an example of this here would be 3 to the x. We can't have a variable as an exponent. Thus, for this last one here, we would be talking about exponential functions. Bottom of a fraction and negative exponents really are both talking about rational functions. And our fractional exponents and radicals are both really going to be radical functions. So if a function makes one of these true, or makes one of them false, then it's not going to be a polynomial function. So let's take what we've covered so far and put it into practice. And let's see here. Now in each one of these example problems, we're going to do several things. One, we're going to decide whether or not it is a polynomial function. If it is, we want to write it in standard form. State its degree, type, and leading coefficient. So let's look at A. Negative 2x to the third plus 5x plus 8. We first need to determine whether or not it's a polynomial function. So let's go through our list that we have. Are there any negative exponents? No. Are any exponents fractions? No, so we're good there. Are any of the exponents variables? No, so we're good. Are any variables inside of a radical? Do we have two variables being multiplied together? And are there any variables in the bottom of a fraction? So is this a polynomial function? Yes. Now we do need to write it in standard form. So the biggest exponent would go first and then decrease. Well, is this one already written in standard form? Yeah. So we can just go on and rewrite it as is because we do have x to the third, x to the first, and our constant term. The powers of the variables are decreasing from left to right. Now, what would the degree of this be? So the degree would be 3. Because the biggest exponent is 3, the degree would be 3. Now, what would the type be? Cubic. Bless you. Since it is a degree 3, degree 3s are considered to be cubic functions. Now, the last thing we need is leading coefficient, which would be negative 2. Because leading coefficient is always going to be the number in front of the variable with the biggest exponent. Since x to the third is the biggest exponent, the variable with the biggest exponent, the number in front of it is negative 2. Questions on this here? Let's look at the next one. Let's look at B. Can we say that this is a polynomial function? So let's go through the checklist and make sure. Are there any negative exponents? Are there any fractional exponents? Are there any variables as an exponent? So we're good there. Are there any variables inside the radical?
Yes.
I mean, it looks like this here could be inside of the radical, but the radical does stop at the 2. It does not include the x to the fourth. Now, if it did include the x to the fourth, if it did extend out, can I take the square root of x to the fourth? Because that would be x squared. Because x squared times x squared would give me the x to the fourth. So it would still simplify and work. But it's not included. So we're good there. Are there any variables being multiplied together? Well, no. We don't have two different variables being multiplied together, so we're good there. Are there any variables in the bottom of a fraction? So is this a polynomial function? Yes. Is this one here written already in standard form? No, because we need the x to the fourth to go first. So we would rewrite this moving the square root of 2, x to the fourth first, and then negative 0.8x to the third minus 12. Because we want the variables ordered from left to right, from biggest to smallest. What would the degree for this one be? 4, because the biggest exponent on the variable is 4. Now what would the type be? Yes. Quartic. And the leading coefficient. Almost. The square root of 2, yes. Because we're looking at the number in front of x to the fourth. And that's it. Any questions on A or B? Okay, let's look at C. Why not? Because we have x to the negative 1 here, this would not be a polynomial function. Not a polynomial. And that's all we have to do here, because as the direction said, we only had to state it in standard form, state the degree, type, and leading coefficient if it was a polynomial function. Since this one here is not a polynomial function, we can just write it's not a polynomial function and we are done. Let's look at the next one, letter D. Can we say that this is a polynomial function? Why not? Yep. 3 to the x. This here would make it an exponential function. So this here is not a polynomial function. Any other questions on these here? The 3 to the x. We can't have a variable inside the exponent or as an exponent. Because what this will make it is into an exponential function. The x squared part is a polynomial function, but the x to the third makes it an exponential. Any questions on this here? Do we need to see another example of one of these? We feel comfortable with these here? Okay. Let's look at the next part of the lesson, evaluating a function for a given number. Evaluating a polynomial function. Well, whenever we evaluate a polynomial function, we're taking whatever is given to us and plugging it in. So here we're plugging in 3 for x. So we're finding f of 3, which is really telling me that every place that there's an x, I'm replacing it with a 3. So we'll have 2 times 3 to the 4th minus 8 times 3 squared plus 5 times 3 minus 7. And well, at this point here, we can do what? We can plug it into a calculator, and it'd give us the answer. Because if we did this by hand, well, we would take 3 to the 4th, which would be 81. 3 squared would be 9. 5 times 3 is 15 minus 7. Well, 2 times 81 is 162 minus 72 plus 8. Well, 162 minus 72 is 90. And 90 plus 8 is 98, which I think some of you already found. Yes? For those of you who plugged it in. And that's it. That's all we have to do for this here. Any questions on this problem here? Well, let's look at the next one. We'll look at this one here. Negative 2x to the 4th plus 6x to the 3rd minus 3x plus 11. We're going to evaluate it when x is 4. Clear. I'm going to use the calculator for this one here. Now, the way that we can plug this in is go over here and type negative 2 parentheses 4 close parentheses to the 4th plus 6 times 4 to the 3rd minus 3 times 4 plus 11. And this is how y'all typed it in and went on and hit enter. And we agree with negative 129. For those that typed it in? Yes? Okay. And that's all we need to do. Now, I have a feeling most of y'all, well, we've noticed it here, but also on the yellow calculator, that we can type an X into the calculator. But both me and Miss Kendall told you don't be using that, especially when we're typing stuff in. And that's because for this here, and the way this is what we're doing here, the value of X for these calculators need a value. They actually need a value for it. And we could actually plug it in. Because the store feature right above the on button, the STO is store. So if I wanted to, what I could have done is I could hit for store X. For store X. And what that's telling the calculator is that I want it to store 4 into the value of X. So from now on, I'll go on and hit enter. Whenever it sees X in a calculation, it's going to think of it as 4. Now this doesn't affect graphing when we graph a function. It just affects it when we type it in the home menu. So what I could do now is say negative 2 x to the 4th plus 6 x to the 3rd minus 3 x plus 11 and hit enter. And it'll give me the exact same thing because it understands that X is 4. Now, for the most part, if we're doing just one calculation like this here, that's not a big difference between plugging these two in. But say, for this function here, I didn't want to just know what the value of 4 is, but negative 4. I wanted 4 and negative 4. Well, at this point here, I could say negative 4, store X, enter. Well, now what's the value of X? Negative 4. It's easy as negative 4, yes? Now, I could go back and type the whole thing in. As we've seen with the calculator, is if I cursor back up to highlight the problem and hit enter, it brings it back down, yes? And if I hit enter again, negative 873. Well, that's a lot faster, isn't it, than retyping it back in? Because we can continue to do this. So I could say negative 25, store X. So now it's stored it as negative 25. I can cursor back up to the problem, bring it back down, hit enter again, and I have it. So if I'm just trying to find one value, really either way doesn't matter. But if I'm having to calculate multiple values for the given function, we can do this very easily with the store. But you do have to be careful on making sure we're storing the correct value. Now this is also helpful, especially when we're plugging in a negative number. As y'all have seen before, if we forget to put the parentheses, it can sometimes change the value. Here, because we stored it as X, we don't have to worry about it because the calculator is taking care of that for us. Any other questions on this here? There are no questions on that. We're going to look at this here. Now, in behavior is the last thing we're going to look at today. In behavior, what it's talking about is what is the function going to do eventually in either direction. And it's one of 4 options that we can have. Let's get a highlighter. Now what happens in the middle for each one of these functions will be different. But no matter what the function is, it will eventually end up doing one of these 4 things. Now, when we looked at quadratics in chapter 3, they were all what? U-shaped graphs. Yes, either both going up or both going down. Now, a quadratic is degree 2. It's even, yes? Well, it works out that any even degree polynomial will eventually have both sides going up or both sides going down. And really, if it's going up or down, is really dependent on the leading coefficient being positive or negative, because we only have those two options. Now, it's either going to work out that the degree is odd or even. Odd, odd. And the leading coefficient is either going to be positive or negative. And it fell asleep. Now, for the first one here, we do have that weird notation, f of x arrow plus infinity as x arrow negative infinity. F of x arrow negative infinity as x arrow positive infinity here. What this is saying, so this part here, all right, with the highlighter, is saying that as x increases, as the values of x get bigger, the function f of x is doing what? It's decreasing. It's going to be a bigger negative number. So as x increases towards a positive number, the function itself, f of x, is going to a negative. As we get bigger and bigger negative values for x, the function itself is going to positive infinity. And that's all it's saying. So if we look at odd and positive, they're saying that f of x approaches infinity, positive infinity, as x approaches positive infinity, and f of x approaches negative infinity as x approaches negative infinity, and that arrow is just talking about approach. Now, if it's odd and negative, f of x approaches negative infinity as x approaches positive infinity, and f of x approaches positive infinity as x approaches negative. And for when the degree is even, they're going to end up going in the same direction. So f of x approaches positive infinity as x approaches positive infinity, and f of x approaches positive infinity as x approaches negative infinity. And lastly, f of x approaches negative infinity as x approaches infinity, positive infinity, and f of x approaches negative infinity as x approaches negative infinity. And with any of these here, if the degree is even, well, the end behavior is going to go in the same direction. If it's odd, it's going to go in opposite directions. Now let's actually look at an example of this to see what we're doing. And it's not as complicated as you might think. So when we look at this first one here, describe the end behavior of the graph. What is the degree of this function here? 4. And 4 would be even, yes? Because 4 is an even number. Now what's the leading coefficient? Well, it's our negative 0.5. So it'd be negative, yes? So looking at this here, we do have an even degree function and a negative leading coefficient, yes? So if I look at my chart, even and negative, we have this bottom one here. And what it's telling me is that f of x approaches negative infinity as x approaches infinity. And f of x approaches negative infinity as x approaches negative infinity. Yes? Any questions on this so far? That's it. That's all it's asking for. That is the end behavior of the function. So really graphically what it's saying is somewhere on the graph we have a function that will eventually do something like this. It might do some different things in the middle, but eventually both sides are going to go down. Question? Yeah, so it's just looking off the fact that the degree is even and the leading coefficient's negative. So it's really based off the graph. Questions on this here? Let's look at the next one. So since we're looking at in behavior, we need degree and leading coefficient, see what they are. So what's the degree of this one here? 3, which would be odd. And the leading coefficient, which would be negative. Because since we were really just trying to see is it odd or even, positive or negative, we're just taking these parts here. And now we can look at our chart. So odd and negative, well, that tells me that f of x approaches negative infinity as x approaches infinity. And f of x approaches infinity as x approaches negative infinity. That's it. And really with all these odd, if the degree is odd, then behavior is going to be going in opposite directions. If the degree is even, they're going to go in the same direction, both up or both down. Questions on this here? Let's look at the last one. So the degree for this is 3, which would be, and the leading coefficient is 0.25, which would be positive. So odd and positive would tell me that we would have f of x approaches infinity as x approaches infinity, and f of x approaches negative infinity as x approaches negative infinity. Any questions on any of this here? We good with this here? Now I know that's the end of the note sheets, but I want to do one more thing. I want to make a coordinate plane. And let's now with this graph here, we can't tell anything about it number-wise because we don't know what the graph is and we have absolutely no scale for anything here. But what could I say about the degree? What kind of degree would we have? Odd or even? Because our end behavior for this here behaved in one of 4 ways, didn't it? Because if it's even, what is the graph eventually doing? It's going in the same direction. Either they're both going up or they're both going down. Odd, what happens? They're going in opposite directions, yes? So, if we go back, what can we say about the degree of this function? It's odd. Now, the leading coefficient, we can't actually say what the number is because we don't have any numbers anywhere. But what could I say about it? It is negative. Because when we look at the graph, as x becomes a smaller number, the graph is going where? Up. And as the graph becomes bigger, the graph is going down, which is the setup for our odd and negative. Let's look at another one. Degree would be And it would be negative because the graph is opening down. Now this here could be x squared plus 4. Because this would be a function that would be similar to what we're looking at. Or we could actually have x to the 6 plus 4. It would behave in the same way. Now, the big question is kind of why is this important? Well, let's just say the following polynomial that I'm going to draw is even, and the leading coefficient is positive. So we're saying that we have a function that we know the degree is even, and the leading coefficient is positive. We plug it into the graphing calculator, and it gives us something like this here. What do we know about even and positive is that they should both go up, yes? But where is this one going right now? So if it's supposed to be even and positive, what's this side have to do? It's got to go back up, yes? So that means somewhere over here, that graph is going to turn and come back up, yes? Now, the reason that this is helpful is, well, when we think back to quadratics when we were solving by graphing, we were trying to find the values or the spots where the graph crossed the x-axis. Because any spot where it crossed the x-axis was a solution, yes? Well, by knowing that this is even and positive, I know that this has to come back up and cross the x-axis at some point. Well, that means that if I'm looking at the graph for values, I need to move over because there should be another solution somewhere over here. And really knowing even and positive, or knowing these here, how it's supposed to behave as we extend it out further and further, will help us see what the solutions are, even if they're not given to us in our little screen. But that is all we are doing today. Your assignment is on 172, 3 through 6, 9 through 14, 17 through 19, 21, and 22.